I am Carl Churchill. I'm a graphics reporter with the Wall Street Journal, and I use Blender a lot. Blender is a free software that is great for making 3D maps. A lot of this can be credited to tutorials like Daniel Huffman's, it's right there, which remains an essential primer for the standard Blender mapping workflow. You can generate maps like this after a bit of practice, and they work fine, but by applying some tips in Blender, you can get some impressive results. I'm not going to be going into every detail of how this render was made, but I'm going to try and cover as many of them as I can, and ultimately the goal is to show what is possible. But let's see first if I can recap the basic Blender workflow in just like a minute to give a quick sense of the process. And if you want to get more into the details of how this works, I think Rosemary's talk later on today is going to be like a better primer of this. She's giving me like this hand. You take a DEM, you export it to Blender, you displace a plane by the elevation values of that DEM to produce a model of the landscape, you texture it, you line up your camera, and you're set for rendering. But how can we push Blender to do more? Well, the caveat first is that I don't know everything, and a lot of this has been kind of figured out on the fly over the past year or so between me and Daniel and a bunch of Slack threads. My first question, though, is how can we know that a mountain in Blender is going to be as high as it is in real life? Which is what I got a lot from my editors when I started to use Blender for stuff at work. Because obviously, if you crank displacement up a lot, you get nice shadows, but that's not how it actually looks. As an example, this is Mount Blue Sky outside Denver, Colorado. How could we make a model in Blender that was like actually as high as that mountain was in real life? It's best now to think of a physical model that we're building, and like any accurate model, you need to be able to transpose a real-world value down into a differently sized world. Now be warned, there's a lot of math incoming, and it's unavoidable, but we have a clear goal to keep in mind. We need to find the dimensions of our space in reality and in Blender so we can stretch our model to an appropriate amount. And this transposition involves understanding more about what the displacement node actually does. And again, I need to credit Daniel Huffman here in particular for helping me sort through all the math here. The trick is, Blender is interpreting height differently than you think it is. The height is a value in Z space, but that value is displaced from the mid-level by a percentage of Z. So a scale value of 1 doesn't mean anything in reality. It is only valid for the size of the plane inside Blender, which has no connection with the size of the area in reality you are mapping. So we need to identify what that percentage is to put in as our scale value at the bottom, which means we need to know how large a real-world space is and then how much vertical space we are covering as well. So your default Blender cube is 2 meters wide. Scale and width here are different things. So its scale is 1, but its width is actually 2 meters. Because it's 1 meter on each side of the 0 point. That means its Z scale is 100% of 2 meters inside Blender. And that 1-to-2 ratio in general, for some reason, holds true for basically most things. Like we're kind of still figuring it out, but it seems that that just kind of works for some reason. But what does that 2 meters in Blender correlate to in reality? And then what percentage of that real distance is our elevation range? So I happen to know that this area I cut out in QGIS is about 40,000 meters wide at its lowest point, is about 40,000 meters wide, and its lowest point is 1,790 meters, and its highest is 4,325 meters. If we take the difference between those two, we get 2,535 meters of vertical range. And if we divide that by our width, we get 0.062, which means that out of 100% of a cube made up of our terrain, 6.2% of that space would be taken up by our vertical elevation range. And all we need to do in Blender is create a map range node, map our lowest and highest values to that 0 and 2 ratio, and then take that percentage of 100, the percentage of 1, and we plug that into our scale. And it looks pretty believable. If you want to verify it, you just calculate that ratio precisely of what 1 Blender meters equals in real world meters. And if you place a plane at the Blender equivalent of the summit, it should sit right at that line. But if we're pushing for realistic height, why not go for realistic light too? Fortunately, Blender has a built-in optional plugin called Sun Position that does exactly that. You just put in the coordinates of your area, and you can get the accurate sun position for any time of day, and you can even adjust it by time zone, or even animate a full day cycle inside Blender. But let's go one step further and talk about water, which means we need some terrain that actually has water. This is a slice of a topography layer with a 3D ocean floor. What if I wanted a horizontal ocean surface over that actually looked like water? Which means we need to know where that water line is in 3D space. But we can use all the information we would have needed to make this terrain to calculate that. By just reverse engineering where 0 is in relation to our vertical range, we can work out what that means in Z space inside Blender. And I know this is a lot of numbers. But that's why I'm putting it on a slide where you can parse and reference through it on your own time if you want to. But the gist is, by taking that final number and plugging it into our Z location, we can make a solid body that clips with our DEM right at where the shoreline is. Oh, and by the way, if you can guess where this is, you get a muffin. So, who's it? Tom gets a muffin. I heard it first. But how can we make it look like water? We have to remember Blender scale is not real world scale. Water looks different at different scales. At a map scale, it will be almost completely opaque. That's why in a satellite image, if you look at the ocean, it basically looks black, but in a pool, you can see the bottom. I mean, hopefully. Water shaders are an entire world unto themselves. And this talk is not going to get into the way that shading works necessarily in Blender. But I basically just use a combination of a glass shader, some opaque ones, and then an internal space of particles called a volume to simulate the internal and external properties of a large area of water. And if we apply that to our cube, to our rectangle, we get a nice realistic looking ocean. But because water at this scale is practically opaque, we can't see our bathymetry anymore. This is a reminder that realism isn't necessarily clearer, and it's not necessarily better depending on your needs. I think it's good to go towards realism so you know you can do it, and then work your way backwards to what's actually best for your audience. We can just adjust the shader by tweaking some of these knobs, letting more of our glass through and less of our opacity, and we get a less realistic but more informative peek through our water towards the bathymetry, but we still keep that nice flat surface. If we combine our tricks from the presentation so far and some other stuff, you can end up with something like this. And I know I didn't talk about the clouds, because that involves explaining 3 other things that this presentation is already at 52 slides. But everything I already talked about will get you to this point, and it's all possible inside Blender right now, which again is free, journalists. Hopefully this gives you at least an idea of what is possible and inspires you to push the bounds of 3D more. Any questions? So, should I just repeat the question? Yeah. Oh. So the question was, if I use a realistic sun angle, would I just create relief inversion? And that is true. And again, it depends on what you're doing it for. If you're doing an overhead relief, maybe a realistic sun angle isn't appropriate, but most of the time, when I'm making a map of a place, I'm doing it in perspective view, and I would rather the light to hit it in a realistic way, because I think it has all sorts of minor, secondary. I think it's going to be easier to make it look realistic with the realistic sun position than to lock it to the cartographically optimal sun position in a perspective view.
Hi, Carl. I was wondering if you have had any experience working with the GIS for Blender plugin, and how, if so, how that interacts with or even takes care of some of the workflow number crunching that you have to do with Blender with your current, workflow. Yeah.
That is a very good question. For those of you who don't know, there is a Blender GIS plugin. I don't use it. In the past, like a couple years ago, I tried to use it, and I just found it unusable. I found it very janky. My understanding is that it has improved a lot now. I think it's really good for loading in like vector data into Blender. I personally still prefer doing it kind of the more analog way because it's more restricted to just like the most robust set of Blender features. And I think you kind of have more control over every aspect of the process. My hunch is the Blender GIS will be able to help with like ingesting different data sets and stacking them on top of each other. But if you just want like really realistic terrain maps, I would still stick to like the most like simple environment possible, so you have the maximum amount of control.
We can do one more quick one if anyone has one more.
So where's your favorite spot to get the map texture like imagery?
So it depends. The quick gist of it is for the DEM, I have an open topography plugin in QGIS that I just like zoom in on my canvas, get like a NASA DEM, and then you can follow Daniel's tutorial to like learn more about the exporting process, and then you can also like ask me and I can give you more information about that. In terms of like imagery, for the US, USGS NAIP is really great ortho imagery to use. Sentinel-2, which you can access through the Copernicus browser for free, is really good to use. I often use Google Earth Engine to make mosaics. And then normally for like demos, I'll like use like a WMS of like Google imagery and then replace it with something else later on for like licensing reasons, just to give me a sense of where it is. And also, honestly, natural Earth like base maps are really good to use for like big regional swaths.